Hey everyone, and welcome to this explainer. Today, we're skipping right past those surface-level definitions of artificial intelligence, and we're diving straight into the mechanical elegance of how it actually works. Look, as enthusiasts, we all know there isn't some literal digital consciousness floating around inside our laptops. But let's be honest, the exact nuts and bolts of how a system processes data can still feel, well, kind of elusive. So we're going to break down how a neural network functions step by step. We'll use foundational concepts from our sources to really expose the rigorous architecture driving the outputs we see every single day.
You know, it's incredibly easy for the mainstream to fall for this cultural illusion of digital magic, right? Imagining AI as this unpredictable, almost synthetic entity. But the reality is way more grounded and honestly infinitely more fascinating. AI is built on a highly structured, rigorous mathematical architecture. Think about it. When an AI recognizes your face to unlock your phone, it's not looking at you. It is running your image through a colossal sequence of matrix transformations and vector spaces.
All right, part one, the ghost in the machine. Let's look at how neural networks process complex data using pure math to simulate actual understanding. To really frame this, we're borrowing a brilliant approach highlighted in our source material, leaning into the visual intuition championed by educational creators like 3Blue1Brown. Because instead of just talking about data in the abstract, we're going to conceptualize the geometry and the literal flow of that data. We're going to watch how numbers physically navigate through the interconnected layers of a system. Once you start visualizing these matrix transformations, I promise you, the underlying mechanics suddenly make total sense. Moving right along to part two, the flow of information. We're breaking down how systems transition from basic inputs to highly confident predictions. Okay, I want you to imagine for a second that you are a single data point. Let's say you're a single pixel in a photograph of a handwritten number 7. Your journey is going to follow 5 very distinct chronological steps. First, you, the input image, enter the system. Second, you get multiplied and added together with a bunch of other data in a stage called weighted sums. Third, that combined result passes through an activation function, which basically decides what happens to you next. Fourth, the system takes a guess and runs a comparison with the result. And finally, step 5, the holy grail, the learning phase, backpropagation. Every single cycle of machine learning follows this exact sequence, no exceptions. Now, the absolute most critical point in that journey happens right after the data enters the system, when it hits those layers of weights and biases. These aren't magic. They are just essential mathematical variables. The weight decides how important a specific piece of data actually is, while the bias acts like a threshold, shifting the activation function to make sure the math aligns perfectly. As your little pixel of data travels deeper and deeper into the network, it gets multiplied by these weights and shifted by these biases literally thousands of times. And that massive chain of math, that forms the entire basis of the network's ultimate decision. So after bouncing through all those mathematical filters and passing through an activation function that decides if the signal is even strong enough to trigger the next neuron, the machine finally spits out an answer. It says, okay, I am 90% sure this image is a number 7. Which brings us to the absolutely crucial moment of comparison. Did it get it right? If we fed it an image of a 7 and it guessed 7, boom, the system succeeds. But what if it guessed it was a 2? Well, this is where the concept of a loss function steps in. It's simply a mathematical way for the AI to measure exactly how wrong its guess was. Which brings us to part 3, backpropagation. This is the learning step where the network actually corrects its own errors by tweaking those internal variables. All right, time for a quick pop quiz. If the network realizes it made a mistake, how does it actually fix it? Think about what is literally happening under the hood when a massive network backpropagates. What is the actual mechanical definition of this process? Put simply, backpropagation is the machine grading its own test and then studying what it got wrong so it does better next time. When the network guesses a 2 instead of a 7, it sends a signal in reverse, all the way back through those layers of mathematical filters. It calculates exactly which weights and biases contributed to that terrible guess. Then it turns this dial down just a little bit, and it turns that dial up just a little bit. By continually adjusting these internal variables to minimize that loss function we just talked about, the network ensures that the next time it sees that specific image, its probability of guessing 7 goes way up. Guys, that right there, that is the literal engine of machine learning. And finally, part 4, the mathematical foundation. These fundamental principles form the essential bedrock for all of these complex calculations. So we've established the architecture, and we know the sequence of how it learns. But what are the actual engines powering all of this?
What specific branches of mathematics can handle organizing massive grids of numbers while simultaneously finding the absolute optimal rate of change to minimize errors across millions of different variables?
The true engines driving the whole shebang are calculus, linear algebra, and just massive, massive amounts of data. Linear algebra is what allows the computer to organize and calculate millions of weights and biases all at the exact same time using vast matrices and vectors. Calculus, specifically the chain rule for those keeping score, is what powers that backpropagation. It allows the system to calculate exactly how much to tweak each individual variable to minimize its error. When you take the rigorous math of calculus and linear algebra and you apply it to a totally unprecedented scale of data, the result is just astonishingly capable.
Let's wrap up this explainer by turning the mirror back on ourselves for a second. We've mapped out the machine, right? We've seen that artificial intelligence learning is fundamentally just calculus and linear algebra, mathematically adjusting to errors over and over and over again. But if a purely mathematical architecture can learn to recognize a face, or translate a language, or write complex code just by iteratively correcting its mistakes, what does that say about human learning? Are our biological brains doing something fundamentally different? Or are we just walking around running our own unimaginably complex, wetware version of backpropagation? It's a pretty wild question to chew on as you explore the AI tools evolving all around us. Thank you so much for joining me, and keep questioning how the world really works.